everybody. Just doing the last project, the graph assignment. Um, I'm going to go through real quick the code. We'll run it, and then I'll explain what it's doing in the end. I have a couple things to submit. I have the main CPP, which has got everything on it. I'm doing prims and Kerskal's minimal cost spanning trees. Which a basic way to describe that is to pretend that you have, um, let's say you're one of the contractors out here that's making the pop-up home neighborhoods, and you have to go around potential plots of land that you want. So you'd plot your points, be like, I need to get from here, here, here. What is the best distance for that so that the roads aren't designed with abnormal length to them, and it's going to be the minimum weight cost. So spanning trees have weight to them. They're unidirectional. The minimal cost is going to find the most ideal, shortest route to touch all of the points that you would want as this contractor. You want to touch all the points because they need to go there because you need to get a road there, with the least amount of distance between them. And so you'll have an ideal optimal road as far as distance goes, or weight in this case of the spanning tree. So you'll see it come to fruition at the very end when I draw out what the points are plotted, or what the points are saying. But for now, let's just go over some quick things. So I have a really big thing here. I'm initializing x, basically my infinity value, um, to my int max, which is declared basically as infinity, right? Um, then for Kerskal's only, I did two functions, combined and search. We'll go over those as they get down there. But I start right off the bat with a graph structure. So we're gonna look at prims first, and you're gonna see on how hefty it is. Let's see if I can zoom out just a bit. So that's what it looks like. You've got your x, your y, or however you want to do it, numbers over the top, down the side. Um, and then that's what this looks like. These are all of the points. If you were to have a spanning tree, this is what mine looks like. You know, so just as an example, all in C at least, all the lists start with index 0, right? So you notice the first column and the top column are all x's, they're nothing. But then over here, 1, which would be my first thing over here, 1, 13, and 2. So if we go to 2, right? 2. And then if you go down to 13, the value is 13. It just happened that they happened to be that. I did a random number generator, and that's what popped out. So that's funny. I didn't even notice that till now. But same thing if you go to 2. If you're going to go 2, you can see 2 from 1, right? 2 from 1. And you can see 45 for 3, 3, 45, 2. And then 89 for 14. So 14 would be down here, 89. And so that's basically how that looks for the prims one. It's much larger than the next one I'm about to show you. So if we keep scrolling down, and this is, in essence, the same exact thing minus the infinity in here, right? So we assign everything that we haven't been to in Kerskal's infinity, but we don't do it manually, almost like this. This is like a hard code version of it, and then this is done through initialization. But we do have to hard code all of these points anyway. And if you see here, so 0 and 1, x, y. Okay. 1, 2, 2, just like in this array. And then 1, 2. Oh, the value's 2. 1, 13. 1, 13. Bam. Value 13. So just like that. So I'm using the exact same graph for both of them. The reason I'm doing this is so that you can see that two different graphs, with the same purpose, right? Minimal spanning tree purpose, trying to find the best road structure for this neighborhood that we're building, right? how these two different algorithms can produce the exact same thing. Good to note is that even though this is a hard-coded structure right here for prims, it's a n log n, which is over time better than n squared, right? Because the curve for n log n is flat and it just goes, and then n log n, as more information and time get put in, it curves up, right? And Kerskal's is an n squared. So just keep that in mind. I won't be able to show you the official memory in here because both of these are on here, so it's going to take into account both of them as far as the entire process. If you really wanted to, you could just, because I have them all labeled for prims versus Kerskals, you could just comment out one or the other and test them individually. Also, we have the solutions. So these are the arrays that hold all of the answers. And what's so for prims, we have a what's near to something that's already in the solution. So it's like, all right, we have 0.12. What's next to 0.12? That's the nearest. Oh, it's this one. Is it connected? No. All right. Is it this one? Is it connected? Yes. And then, all right, this point. What's the next one? So that's what near holds, right? Solution holds the actual points, the 1, 2, the so on and so forth. This holds the value of the point that's next. The next point ready. So, continue on. Now we have the Kerskal's solution. Um, Kerskal is going to have a disjointed socket, or sorry, not socket, subset. And all this is doing is so that if you look at the graph, for both of them, prims naturally doesn't do this because it's got the infinity. I've visited that already kind of a deal. I know the value. So we're either going to reset the value or we're not going to visit something we've already previously been to. But with Kerskal's solution, we have to prevent it from doing this. The 2, 3, 14, 2, 3, 14, if it were to line up with the numbers correctly. But we have to make sure it doesn't cycle. And so the disjoint subset basically just says, have we visited that? Don't do that. Don't do that again, okay? Because we've already been there. Visited points are also logged in here as another precaution. So this is just going to say we don't want to go back, but we know the value. And this is going to actually just put in the point that we've already visited. So that way it's doing basically what the near array is doing. It's near to something we've already visited. So, and then the solution for this array, it's same thing, just named differently. It's going to do the exact same thing, hold all of the points that are our answer, right? And it's basically a two-dimensional array that holds x and y, and has 36 out so that it has the potential of holding, the max number of points, whatever it is. Let's see. Also, I included a bonus prims 8 number spanning tree. So if you wanted to, you can literally just comment out these two lines up here. Comment those out. Run the 8 one. It's a little bit simpler. You can understand it a little bit more clearly what's going on, how it's doing its thing. Uncomment these. And then you should just be good to go. And obviously comment out the big prim structure right here, the 20 by 20. So that way you can run the smaller version if you want. But let's get into main. So if you see here, prims, minimal cost, you have a bunch of loop variables. I'm not going to get into all of them because it's just too much. But we have basically the function of it of find the minimum cost edge. It's going to simultaneously go through x and y, find the value that they pinpoint, right, like on a spreadsheet, and go, all right, up over 2, right, and then bam, got that. In this case, it's going up and over the same amount of numbers, starting from 1 because we're not using the 0 index. And then what it's going to do is it's just going to take the minimum value that's equal to the new value and then mark the start and the end of the edge and then just load that up into the solution set right here. And then it's going to start searching and it's going to mark this as our start, right? Our start for what's near, so that way we're not accidentally going someplace that we've already been. And it's going to just search for the next one. It's going to identify the nearest point to the current one, It's going to go through, reassign that edges, rinse, wash, repeat all the way through. It'll include the rest of the edges in there as infinity, and that's what it's doing here. So that way it can continuously search through and find the next value. This is updating all of the solutions and the near arrays so that the points, every time it goes through it loads that up. Or this is the actual piece that's doing that, the updating. This is the piece that's adding the X and Y solutions to it. And then it just displays it to the user. And then I have the weight, which takes all of the solution points, right? All the points in the solution. So 1, 2, 14, 13, whatever's in there, you'll see in a bit. And it adds the weight of the edges. So if you look on here, the weight is 45, 2, 89, 7, 12, right? The weight is the distance in between. And so it's going to add up all of the values of the tree. And basically, this tree is going to, it's not from point A to point B, so it's going to look wonky, but it's going to touch all of these points, right? Minimal spanning trees, how do I touch all of these points with the minimum amount of distance weight in between? And so it's going to span out from a tree and basically show you all the paths that you have to take that are the minimum weight of this graph. So that's what that's doing right there. Is just adding, you know, each time the new weight of each point that's in the solution, and then it's just displaying each point in the solution, and then it just prints out the actual weight. So big thing to note before we get into curse goals. So with prims, what it does is it goes, all right, find the first minimum weight, right? So 2. So 0.12. Okay. So what's next on that that we're gonna do? We've been to 1, so we can't go to 1. We're gonna go to 89. 89 is really a heavy number, so we're gonna try 45. 45 is the less of the 2. We'll go here. Okay, so we've been to 2, 14, or sorry, 4, 14, 7, and 88. It's going to choose the 7, right? And continue that process from where it's been all the way until it gets into it. So that one, in essence, it seems directional, but it is undirectional, but only because once it gets to a point, it can start from another section, as long as it just doesn't go to a point that it's already been to. So usually it branches out from one specific instance, but that's just a thing to note. As where the curse goal is just going to find, all right, 1 to 2, that's the lowest one. All right, what's the next lowest one? Oh, 6. 6 the next lowest one. All right, let's do that. Okay, what's the next one? We have a tie between 7, 7, 7 right there. There's a lot of 7s in there, huh? All right, so we'll just do this one. Next one would be 7 again. Okay, next one would be 7 again. And so it will make the same tree. It'll have the same weight. It just finds it differently. It will find the next minimum until it's reached its solution. Every point has been touched with the minimal distance, right? Same goal, different style. As where one goes from where it was last, the other one goes just to the next one. That's the minimum. All right. But what does it do? So basically, same thing. Almost the only difference is that you need to know the edges for this, including the points. And so it's going to scan through all the edges, get them all. It's going to initialize them all to 0, right? That's what we did there. And then it's going to go through and find the minimum cost edge, right? It's going to go through each edge, find the minimum cost, and then it's going to assign the front and back of the edge, right? 1 to 2. We'll just keep using that 1 to 2 since that's the lowest in mine. Set them to start and end of the edge. Set the minimum value to the new value, and then just set the point to the new point, right? And then what it's going to do is going to make sure that it doesn't cycle, right? So it's going to be like, should we even include this? Did we already cycle through this? And it's going to go, as long as the front and the back of the edge aren't the same, or the same as far as a point that we've been to previously, then it should be good. So include it, right? So as long as they're not equal, they should be good. Include it in the solution. And it's just going to do that. It's going to include the point, front, back, and it's going to combine it to the solution set. And we'll look at combine real quick since it's right there. And so all combine's going to do is just make sure that it's not, it's going to check the disjoint array. The negative one's going to say that it's hasn't been visited yet. If it's a positive one, it's going to say that it has been, and that's all that's doing is just setting the 1 to -1 here. Um, and then just continue with the loop. It's going to get visited points. It's going to assign whatever the value was in here, the closest, right? So the point value that we had, which was the visited point right here, it's just going to get assigned 1 to say, yeah, we visit it, and that's going to get loaded up into visited points, which is up top. That way we don't visit it again. Display for each solution in the array. So this is just my display function. Same thing. Fun fact here is because these are identical graphs, just displayed differently, I wanted to show you on how that worked. And so we're actually taking the points that come out of the solution from the Kerskal's solution set, the Kerskal's points array, and we're loading it up into the 20 by 20 up here because they should be the exact same. And so it's searching this graph from the Prim's graph from these numbers that are loaded up once they're correct in the solution array. And so all else fails, they should be identical weights. That's basically what that's saying. The numbers might get identified in different orders, but all of the edges should be the same edges. So if we scroll all the way back down to there, we'll see what happens. I don't think I've actually looked at it, so that's not good. And then it just displays the points and displays the weight. So let's just get into it. And then the search is just here. So this is a collapse find to connect the points to themselves as parents. So all this is doing is just taking the points that are passed into it and just smushing them into the disjoint. Or sorry, the disjoint the subset. If they're not equal to the past value. So that's what's going on there. But let's just do this real quick because we're getting lengthy. We'll run this. I'm all nervous now. Boom. All right, so here we go. So this is our first one up top, right? We'll just do that so you can see it. So the tree weight for prims is 406, right? Because each edge, it's got, I think, 19 edges in there. And then 19 edges in here. And then 460. Bam. And if you see here, 1, 2, 1, 2, and then you're like, all right, cool, that's good. That's good that they got that one. And then 819, you're like, what? That's not there. But if you look, bam, 819. 314. Oh, that's not the next one either. Oh, 314's right there. Same thing. So you're getting the same points. You're getting the same weight. It's just searching for all of the same stuff differently. And so if we keep this up, we'll do the prims one first on here so you can see what it's doing. And what I mean by it's not a point A to B, it's more of a universal kind of I need to get to all these points with the least amount of cost. It's a weight tree. It's minimal cost tree. So let's just do it. So for prims, we're gonna do. I got my marker. Sweet. 1 to 2. So it's gonna go here. Bam. 13 to 1. Bam. 14 to 13. Or yeah, 14 to 13. Bam. 3 to 14. Okay. Bam. 12 to 14. And then 16 to 12. And then 5 to 16. And then 18 to 16. Right? Did I read that right? 15 to 16. Boop. 4 to 15. Oh, look at that. Look at that. 17 to 16. 20 to 6. Boop. I think I skipped 17 to 16. So this one should have been first right there, right? Because it's branching out from these over here. So 19 to 6. 19 to 8. 9 to 8. Or wait, no. 19 to 8 to 19. Oh, 9 to 19. Boop. Okay. 7 to 8. And then we have 11 to 16. Boop. And then we have 10 to 11. Bam. And look at it. If you look at it, all of the points are now connected. You know, and if this were a neighborhood, this would be the most efficient use of, I guess, cost. You know, if we're going to say like cost is asphalt or something, you know, um, for the neighborhood, right? For the plan and the layout. Granted, I know all these are not represented in actual size, but this would be, you know, something that I could see it done. You could do this networking. This is just a interesting thing. So the weight cost here is going to be 460. So all these numbers that are covered now, unfortunately, would be added up to 460. So it'd be 460 weight minimal spanning tree, and that's prims. Prim, boop. And so if you look here, I did have the pattern of going from right to left. I haven't done this specifically with the Kuskalls, but we'll see what it. I know it comes in a different order, but it should be the exact same thing. So make a mental note on that one. Click, bam. Yeah, leave without saving. And then we're gonna go back to edit, draw. So now let's do the Kuskalls. Right, same thing. 460 has a different order though, because it's looking for the next lowest one, right? The next lowest one. So it's going to go, as for this one was going from 1 to 1, you know, and if you look at it, it was going from 1 to 1, and then it kind of crossed over from where it was. This one's going to be bouncing all over the place. So here we go, 1 to 2, 8 to 19, 3 to 14, right? Yeah, 3 to 14. All right, so we want 2, 6, 7. I bet you the next one's what, 4 to 15. Oh, I lied. I guess I don't know, but that's still correct. 4 to 15, and then 13 to 14, and then 9 to 19, 6 to 20, and then oh, that's right, because it's bouncing back and forth to see where it's been. 12 to 14. Right? Is that 12? 12 to 14? Losing my mind. Yeah, 12 to 14. 1 to 13. 5 to 16. There's that big long one there. 6 to 18. Boop. 7 to 8. 6 to 17. 15 to 16. Okay. And then we got. Oh, words are hard. 15 to 16. 16 to 17. Oh, I already did that one. I'm losing my mind. 10 to 11. So another thing is that this one's not in order, so it's kind of driving me nuts. Ooh. Okay. Something's not. That is 4 to 15. Okay, I was like, that one shouldn't be there. And it's not. Okay, so I'm not losing my mind. Sorry, everybody. Bam. Go back there. It's 4 to 15. Okay, so now this is looking more correct. I was like, because there shouldn't be any loops. I thought that was 14 to 15. I'm just making sure real quick that I didn't see a 14 to 15. Okay, so then there should be, where we left off, 10 to 11, right? 12 to 16. Then we have 6 to 19. 6 to 19. Is that real? Yeah, that's real. That's a real one. And then 11 to 16. Interesting. And then where does 17 connect? Oh, 17 to 6. 17 to 6 right there. And so this one found a slightly different one, which is odd because it's got the same weight. It's got the same weight. So I feel like the 6 to 19 is wrong. But unless that's the exact same weight, you know, just a different path somewhere. Should be 17 to a 19. No, there was a 6 to 19 in this one too. Okay. So I might have wrote the other one wrong then. So that is a real path right there. That's real. And that is definitely correct with right here. 19 and 6. 19 and 6. This one's just backwards, but it's the same points because it's on the graph. So, other than that little snag where I think I wrote the 6 to 19, I might have just forgot it, or I might have just overlooked it. But they're on the same points, they have the same values, and they come up to the same weight. So I'm very confident in the numbers. I'm not confident in my drawing. But other than that, that's how these trees work, is they're trying to touch all the points with the least amount of weight in between. And so that's just how I decided to do this project. If you guys have any questions, let me know. Sorry for my weird demonstration and it not being super perfect, but it's right there. It's 916. Sorry, 96 or 196 and 619. They're the same. So I must have just missed that one because I remember I did 26, which was also right here. Where is that? 26, and I must have just missed 619 in the other one. So I apologize for that. But this works. There's no errors. It's good. Feel free to take up the challenge of this one. Because I'm going to post this for students. I know it's towards the end. They're probably like, the last thing I want to do is try and rethink something you've done. But something that really helped me was taking this 8-1 and trying to rework it backwards into a graph, which is not terribly hard. It turns into a 7-point graph, so just keep that in mind. But it definitely was not easy. I'll give you that one. So other than that, I hope everybody enjoyed and have a good night.